Okay, let's just dive right into this. Welcome back to another explainer. Today, we're looking at the absolute ultimate defense system tucked away inside modern electric vehicles. We're talking about the extreme, frankly mind-bending engineering that keeps an EV safe from catastrophic electrical surges. Specifically, we're going to decode the inverter DC-link overvoltage protection system. To really understand the stakes here, we have to ask a pretty terrifying question. What actually happens when an EV motor is spinning at a blistering 12,000 RPM, generating massive amounts of energy, and the high-voltage battery just suddenly disconnects? I mean, think of it like a raging high-pressure river of electromagnetic energy. Now imagine someone instantly dropping a massive concrete dam right in the middle of it. That immense energy suddenly has absolutely nowhere to go. Without a highly specialized defense system, that power will violently tear right through the vehicle's electronics.
So here is our roadmap for today. We'll start with the threat origins, move into software and hardware defenses, check out the DFMEA blueprint, the PFMEA assembly, and finish up with DVP&R validation. Let's get to it.
Section 1, the threat origins. Right, so there are really 4 physical dimensions to this root cause. First up, dynamic regeneration failures. If the motor is spinning fast and the control systems jitter even a little bit, the voltage just skyrockets. Second is the load dump. Imagine the battery unexpectedly disconnecting during heavy braking. That leaves literally nowhere for all that generated power to go. Third, we've got parasitic inductance, where incredibly sudden current changes create these massive voltage spikes. It's honestly like miniature lightning strikes inside the circuitry. And fourth, grounding noise, which can actually completely blind the vehicle's sensors. Less than 100 microseconds. That is the terrifying speed at which this disaster unfolds. When a load dump occurs, the massive demagnetizing energy from the motor floods directly into the DC-link capacitor. Without any warning, a standard 400-volt system can spike past 1,200 volts in the literal blink of an eye. It breaches component tolerances instantly, destroying vital power semiconductors before before even a standard computer processor could process what went wrong. Section 2, the shield, our SWA/HW architecture. To stop a threat moving in microseconds, we need a real-time, multi-layered shield. The hardware operates in 3 distinct steps. First, isolated voltage sensing uses high-impedance resistors to constantly read voltage securely, totally free from high-frequency noise. Second, this info feeds right into a smart gate driver chip. If that chip detects a spike, it autonomously clamps the system to a safe state in under 100 microseconds. It completely bypasses the main processor just to save time. And third, an active fast discharge circuit is standing by, ready to safely vent off any trapped energy. Which brings us to a really critical metric: under 2 seconds. This is all about human safety. If shutting down goes wrong, the fast discharge system forces all that massive stored energy down below 60 volts in under 2 seconds. That's the magic number that guarantees rescue workers, mechanics, or passengers are completely protected from lethal 800-volt shocks. Now, the software part of the shield uses a highly adaptive fallback strategy, reacting dynamically based on motor speed. In the high-speed domain, anything above 7,200 RPM, it triggers a stepwise active short circuit. This intelligently caps the overvoltage peak without causing some massive asymmetric mechanical shock that could, physically break the drivetrain. But in the low-speed domain, under 2,000 RPM, it defaults to an active open circuit. It essentially just lets the motor freewheel so the current safely drops to 0 entirely on its own. Section 3, the DFMEA blueprint. This is how engineers structurally prevent these overvoltage issues before the physical car even exists. They demand absurdly tight physical tolerances. We're talking less than 15 nanohenries. To prevent those vicious voltage spikes we talked about earlier, designers mandate a laminated busbar layout, stacking positive and negative copper plates tightly together. This geometric symmetry acts as literal structural perfection. It keeps extreme physics in check by strictly limiting the total parasitic inductance of the high-voltage circuit. Furthermore, they completely lock down the bill of materials to guarantee perfection. We're talking Class 1 zero-temperature drift capacitors and thin-film resistors with a staggering plus or minus 0.1% precision. This ensures that extreme heat inside the inverter never causes sensor blindness. They also enforce dual-channel active discharge protection and physically limit the permanent magnet flux at the very beginning of the motor design stage, making absolutely sure back EMF never breaches safety limits. Section 4, the assembly, focusing on PFMEA process controls. Because a brilliant design means absolutely nothing if you can't assemble it perfectly, right? Out on the factory floor, there are three primary manufacturing safeguards. First, an absolute ban on manual bolt tightening. It is exclusively done by precision servos. Second, 100% end-of-line calibration for high and low temperatures. This permanently writes voltage sampling corrections directly into the controller's memory for every single unit. And third, extreme dual-stage helium leakage testing to block moisture intrusion down to 10 to the negative fifth millibar. Let's just drill down on that first step for a second, the torque angle method. Why does this matter so much? Well, in an EV pushing hundreds of amps, even a microscopic bit of extra resistance from a manually tightened, slightly loose bolt can cause catastrophic thermal runaway. Using a closed-loop servo to meticulously check both the force and the displacement angle guarantees perfect pretension on every single high-voltage connection. It literally stops fires before they can ever start.
Finally, Section 5, the trial, or DVPNR validation.
This is the ultimate proving ground, where the finished system is subjected to brutal simulated failures. The system must pass exact, unforgiving metrics. I mean, they literally run the motor at 12,000 RPM on a test bench and physically cut the high-voltage battery connection. Boom! The system has to survive this maximum RPM disconnect without ever breaching the 720-volt safety ceiling, all while deploying that active short circuit in under 100 microseconds. They verify the fast discharge drops to under 60 volts in 2 seconds over 100 consecutive times. And finally, they use hardware in the loop to inject physical wire disconnects, ensuring the fault response time happens in under 60 milliseconds. Which really leaves us with this final thought to ponder. As next-generation electric vehicles push past 800 volts and into 1200-volt architectures and beyond, how will these microscopic safety margins evolve next? We've just seen the incredible multi-layered engineering required today just to survive a microsecond surge. It surely makes you wonder what kind of extreme engineering the future holds for us. Thanks for exploring this amazing tech with me today. Keep asking questions, keep looking at the details, and I'll catch you on the next explainer.